Hi everyone! In this lecture, I will show you how we can convert a real-life problem into a system of linear equations. And then of course, I will show you how to solve the system. And here's the scenario that I have made up for you. Okay, suppose we are given three different cities, namely A, B, and C, as you see in this diagram here. Okay, and in A and in B and in C, in these cities, actually, we have some number of people. So in each city, there is some number of people in the beginning, but we don't know how many people are there. Maybe there is no people in one of the cities, or there are equal number of people. We don't know. Suppose in total we have 100 people distributed into these three cities. Okay, here are the rules that we need to follow. On a given day, okay, on a given day, 20% of people decide to stay in the city where they are. So if I am in city A, one of the people in the city A, okay, I can either decide to stay in the city or go to one of the neighboring cities. And the neighboring cities is that if I am in city A, I can go either B or C, okay? And if I am in the city B, I can go either A or C, okay? And this lines that connects two cities together is to represent the transportation link between these cities, okay? A path, just a path that joins these two cities together. All right, and in each city, 20% of people decide to stay in the same city. How about the remaining 80% in each city? And for the remaining part, in other words, the remaining 80% of people, half of them decide to go to one neighboring city, whereas the other half decide to go to the other neighboring city. For example, if I'm a person now who is in city C, I can either go to city B or A, okay, or I can stay in the city. And if there are, for instance, 100 people in city C, 20%, in other words, divided by 5, 20 of them stays in city C, whereas 80 of them goes to cities A and B in the same amount. In other words, 40 goes to A and 40 goes to B. Okay, this is another rule. And the third rule is that a person can visit only one city on a given day. In other words, at the end of the day, you cannot visit more than 2 cities. Okay? These are the rules. Now, this is the situation and this is the rules, and I can also show you, well, I here actually show you in a network like diagram the problem, okay? If I am in city A, 20% of people at that moment, we don't know what the number of people is at that moment on the given day, but what we know is the rate of change, right? We know the rate of the change of people, not the exact number. So 20% stays in A, whereas 40% goes to B and 40% goes to C. And same thing is valid for other cities. If I'm in city C, you see 20% goes to itself, right? 20% remains as they are, as where they are. And 40% goes to city B, one of the neighboring cities, and 40% goes to city A, the other neighboring city, right? And for the city B, the same situation holds. 20% remains, and half of the remaining goes to city A, whereas half of the remaining people goes to city C. Okay, now the problem or the question is this. Suppose at the end of the day, in other words, we take our measurement unit 1 day, so our unit time is 1 day, and at the end of the day, if we have made this observation, suppose we are given the data that the number of people in city A is 40 and the number of people in B is 40 and the number of people in C is 20. So, what is the initial number of people in each city? Here's the question. And how can I find the answer to this question. Okay. Now this is a kind of real life problem, and this is a question that we're required to solve. And the first thing, I want to solve this problem by using a system of linear equations. In other words, I need to convert this problem into that of what is known as systems of linear equations, and then I will try to solve this system by a technique, either Gaussian elimination or Gauss-Jordan method. And I'm given three different values here, right? The number of people in A, B, and C at the end of one day. So actually these are my right hand side values, because to construct such a system I need three different things. First of all, I need the right hand side values, I need the unknown variables, and I need the coefficients, right? And well, first of all, what is the unknown variable here, or what are the unknown variables are here? So we have three unknown variables here because we are required to find the number of people in three different cities, and three different cities means three different unknown variables, namely A, B, and C. And let's suppose that I represent the number of people in A with the variable A, and the number of people in B with the variable B, and with the number of people in C with the variable C for convenience. Okay? And the right hand side values are nothing but values that we obtain at the end of one day. Okay? Our observations, you see, 40, 40, and 20. And each equation actually represents the total number of people in each city. Suppose the first equation represents the number of total people in A. How can we understand that? People can come to city A from either A, B, or C with different rate of change. And how can I find that? What is the rate of this change? Well, I have given the data, so I know that on any given day 20% of people remain in the same city. So if A represents the number of people in A, then 20%, which is, of course, 20% is 20 over 100, and if you cancel out, it is just 1 over 5, and which is equal to 0.2, right? 0.2, or in short 0.2, right? So if I don't know what the number of people at that moment in city A, but I know the rate of change, so 20% contribution, right? 20% of the people in A contributes to the total number of A at that time or on that given day. How about B and C? How about the contributions coming from B and C to the number of A? Okay, then 20% of people prefer at least staying in city B, and the remaining 80%, for the remaining 80%, half of them goes to A and half of them goes to C, which means 0.4 goes to A, right? So there is a contribution of 40% from B to A and 40% from C to A again, right? So this coefficient comes from this fact. So this coefficient, you see, 0.2, 0.4, and 0.4 are found with respect to the facts that we know the rate of change. Okay, how about the total number of P? And again, each cities somehow may contribute to the total number of P. We know 20% of people in A stay in city A, and for the remaining 80%, again, 40% goes to B and 40% goes to C. So 0.4A is the amount of people, or the number of people that contributes to the total number of P. And for the B itself, 20% stays in the city B. So 20% of people on that given day contributes to the total number of B. And for the C, again, 40% of people in C goes to B, right? So this is the way we create our equation. And for the equation, for the third equation, which represents the total number of people in city C, again we just write the rate of change, in other words contributions from each city to the total number of C as coefficients in this equations, 0.4, 0.4 and 0.2 from C itself. Now guys, we have the system of equations, right, where we have the unknown variables A, B and C, which corresponds to the initial number of people in the beginning that is required for us to find, right, because we are asked to find the value of initial number in each city, and A, B, C values represent respectively the number of people in each city. Okay, now we have the system, and it is time to solve the system by using the techniques we know, either Gaussian elimination or Gauss-Jordan. And how can we do that? Well, we can simply convert our system first of all into what is known as augmented matrix form, and I just write down the coefficients and right hand side values. As you see, right, we put our dashed or dotted line to see the fact that values to the right of it are the right hand side values. Okay, and now how can I use Gaussian elimination method? Okay, I check to see whether or not the augmented matrix is in the row echelon form. If it is so, then nothing is left for us to do. We just simply use back substitution and find the solution. But if it is not, we reduce our matrix into the row echelon form, right, the upper triangular matrix form. So I need to eliminate these values I just circled right here. So there are 3.4 values. This should be eliminated. In other words, I need to turn these values into zeros. And again, I apply elementary row operations. I need to replace the second row and the third row just to eliminate the first 0.4s. And to do so, you see, I add the row 2 to -2 times row 1, and then I replace row 3 by row 3 plus -2 row 1. So I obtained the first zeros. I eliminated the first two non-zero values, and then I make my way down. Yeah, you see this value is not equal to 0. We know that for a matrix to be in row echelon form, we need to have a strictly increasing number of zeros from the top row to the bottom row. In the first row we have no zero, in the second row we have 1 0, so in the third row we must have at least 2 zeros. So we keep this in mind and continue to our computation, right, elimination process. And what I need to do is I need to replace row number 3, in other words the third row, by something else, by using an elementary row operation that does not change the solution set. Okay, and instead of our 3, the third row, I added the third row -2/3 times R2 and replace it by it. Okay, how did I understand that? I need to multiply it by -2/3 because, you know, I have 0.6 and I'm looking for the scalar x, so that when I multiply the scalar by 0.6 I need to get 0.4. Why? Because when I sum these two rows together, when I sum them up, the second, I'm of course talking about the second and the third rows, and then this -0.4 value should turn into 0. And how can I do that? If I construct a 0.4 here, right, a plus 0.4 here, and then add this to the third row, then I get 0. So to do so, I'm looking for that x value, and 4/10 over 6/10, and applying the rule of division for rational numbers, then making our cancellations, we got 2/3, right? So we got -2/3 here multiplied by row 2 and added to row 3, and we replaced the result we have found on the right hand side by the third row, and then we obtained what is desired. So now what we have is a row echelon matrix form, right? we see an upper triangular matrix here, a strictly increasing number of leading zeros. So now I can use the back substitution method to find a solution, because we are done with the Gaussian elimination method since we obtained a row echelon matrix. How can we do that? We start with the very last, or in other words, the bottom row. We got minus 1 over 3c is equal to minus 100 over 3. So I found the value c is equal to 100. And plugging it back into the second equation, we got minus 0.6p minus 0.4100, because we found the value of c is equal to 100. And then if you notice, 100 times 0.4 is equal to 40, and you don't forget the minus sign here. When I move it to the right hand side of the equation, we got 0 on the right hand side, so 0.6b is equal to 0. But how can that possible? So 0.6 is a value different than 0. For this equation to be equal to 0, then the unknown variable b should be equal to 0, right? And the same thing for the first row as well. We plug the values of unknown variables b and c we have just found in the first equation, and then we got 0.2a plus 0.4 times the value of c. And I didn't write the unknown variable b again because I know the value of b is equal to 0. So 0.4 times 0 is 0, and I didn't write it in the equation, right? That's no meaning for us. It makes no sense because the value is 0. It has no contribution to the sum, right? So again, 0.4 times 100 is equal to 40, and 40s are cancelled out, and we found 0.2 times a is equal to 0, but 0.2 is a real value that is different than 0, so a should be equal to 0, and that means we have just found the solution to our problem, guys, right? We found the value of a and b's, the two unknown variables, 0, and c is equal to 100. So this is the solution, which means that we obtained the initial number of people in each city, and that means if we want to, what we can infer from this result is, in the beginning there is no person in either city A or city B, whereas there are 100 people in city C. Okay, how about looking at the question in this manner? Now suppose this time we're given the initial distribution. Suppose the initial distribution of people in three cities is the following: 20, 20, and 60. Alright, so in city A, say that we have 20 people in the beginning, and 20 people in city B, and 60 in city C. So how can we find the number of people at the end of one day? Well, I'm saying again 1 day because I take my unit time is 1 day. Okay, my measurement, I make my measurement on a daily basis. Well, it is just an assumption. I can increase or decrease it, I can change it, but I preferred, for the sake of simplicity, our measurement unit is just 1 day. Okay, so well, how can I find that? It is even more simple that, because it is even much more simpler. We don't need to even apply Gaussian elimination technique because we already know the equations, right? Yeah, we know that the total number of A, B, and C, okay, can be represented by using these equations, which we already have created. And by just plugging the values of unknown variables A, B, C that we have at the inception, we can find the number of people in each city at the end of the day. In other words, after 1 day of observation, right? All I need to do is just plug the value of A, B, and C's that is given here, right? A is 20, B is 20, and C is 60, right? For the A, 20% stays in the A, so 20 divided by 5 yields 4. And for the B, 20% stays in B, but the remaining 16 people, okay, half of them goes to city A and half of them goes to city C, which means 8 people contributes to the total number of A. And for the C, right, 12 people stays in C, whereas 24 people comes to city A and 24 of course comes to city B. And for the city B, the same thing, the same procedure is applied, and we got 36 and 36. And I don't need to even find or even do the numerical computation at all, because I know in total we have 100 people, and so far I got 72, right? Adding 36 to 36, or in other words 2 times 36 is equal to 72. And if we have 100 people in total, then 100 minus 72 is equal to 28. So okay, or we can simply put the values back in this equation, in the third equation, which corresponds to the total number of people in city C. Alright guys, as you all see, we can convert a general case problem like this one I just made up for you, and into that of known as system of linear equations, and then I can solve that problem by using a technique that we are familiar with, or with our favorite technique. You know, so far we have learned back substitution method, Gaussian elimination, and Gauss-Jordan methods, and we will continue to learn other different techniques such as Kramer or X is equal to B form, or some numerical approximation techniques maybe, but so far we know this Gaussian elimination and Gauss-Jordan methods, and I applied Gaussian elimination method, which is simple for us to construct, right? To construct the row echelon form of a matrix. Alright, that's it for this time, and see you in the next lecture, guys. And until then, have fun.